Yeah, hello and welcome to my talk about serialization. My name is Florian. I'm with the company MicroStream. Maybe you know the product which was called MicroStream before. And 2 years ago, we moved the project over to the Eclipse Foundation, and we split it into 2 different projects. One of them is the Eclipse Serializer, and built on top of this one is the Eclipse Store storage engine for object graphs. Today, it's all about serialization and where the idea was born for the project and why we did another serializer, because there are a lot of serialization frameworks out there, and why we decided to build another one. It was a decision based on the product we had in mind, the storage engine for the Java object graphs, and there we saw all the serialization frameworks out there weren't sufficient, weren't safe enough, weren't flexible enough, so we decided to build a new one. So what is serialization anyway? Basically, you have 2 parties, either 2 processes or a data store of some sort, and you have objects on both sides, and you have to send the objects over the wire somehow, so you have to create a different format. You have to serialize the object into a format which can be transported over the network and can be deserialized on the other side, at the receiver side. So the Java serialization itself has a binary format as well as our serialization. It's very compact. Binary format, there are a lot of different other ones, of course, like JSON or XML or whatever formats are out there. Most formats have, of course, the pros and cons. But this is basically what serialization is: converting objects into a format and back. Yeah, where is it used? Short answer, almost everywhere. A lot of frameworks you're using on a daily basis use it under the hood without you even knowing it. For example, web frameworks running on a server side store user data on a cache in a session data. You have to serialize it. Most of key value stores serialize data in a binary format. All the caches you use, Spring Cache, Hibernate Cache, whatever. Basically every big framework which handles Java objects uses serialization in some way. So it's a pretty big topic in the Java world. Status quo: Java serialization, yeah, had big design flaws, and Mark Reinhold summarized it in this sentence. And the problem is the serialization is a thing in a JDK which causes problems for current or new features which they are designing. Like the new projects they're bringing in a JDK have to take serialization into account, and that's why a lot of new Java features are taking that long, because they have to support the built-in Java serialization. Yeah, Brian Götz said it as well. They made a lot of mistakes and poses an ongoing tax, and that's the point. All new Java features have to live with it and have to work with it, and that's the problem. Yeah. Security issues are the biggest ones. They fixed a lot of them in newer Java versions, so you can get it pretty safe. But a few years back, you can see on the map global distribution of the vulnerable servers which were running. They were pretty much everywhere. Some framework which wasn't updated properly were running on some server and could be attacked due flaws in the JDK, in the Java serialization. One of the best known ones was a problem in the Apache Commons collections. Apache Commons is used a lot in a lot of different frameworks, mostly as transitive dependency. You get it if you like it or not. And they had a problem where where insecure data could be injected and run or could execute arbitrary code on a server side. They fixed it. Struts had a big vulnerability, a well-known web framework, and there are still over 200 open issues in a JDK regarding serialization and serialization security. It's mentioned ongoing tags, like Brian Götz said. Yeah, the vulnerabilities come from several decisions. So you have the interface Java IO serializable, which every class on a class path which implements this interface, it's just a marker interface with no methods, can be serialized with the Java serializer. And it's pretty easy to inject malicious code into this Java serialization. If you want to see how this works, check out Robert Secord's talks. He can show you live, or he shows live on conferences how to inject code into a serialized format and execute malicious code on a server side. It's scary easy. And this is caused by code execution at deserialization. Meaning if new classes are instanced or created when the data is deserialized, code is executed. Actual Java code, and this code can be manipulated. And that's the biggest vulnerability. Nowadays you can protect your Java serialization by black and white listing, so you can only allow your own types which you can control, which the code is in your hand. And that's a way to get it more secure. So on the other hand, the built-in serialization has limitations. You have to implement Java IO serializable in order to serialize classes. And it has no API contract. Just an empty interface, marker interface, and all the other methods are just magic methods which you have to write into your class you want to serialize or customize the serialization process. Problem is you have code or objects, dependencies from third parties, and you want to customize the serialization. You can't, because you don't own the code. You only can customize your own types, or the serialization of your own types. And another thing is, after deserialization, you always get object copies, meaning if you want to keep two bigger graphs synchronized, every time you send parts or deltas or changes over the wire, you have to merge the changes by hand. You have to know what part of the object graph the change or the delta belongs to. And it's not suited for this use case as well. So it's almost impossible to automatically keep two object graphs synchronous. Yeah, a lot of new frameworks came into on the market, like Cryo, there's JSON, there's JAXB, dozens of frameworks on the market. Some of them are bytecode based, but they make the same conceptual mistakes as the JDK serialization. They have stack depth limitations, and the human readable ones are almost always focused on the format itself. So the limitations are in the format, like JSON is not a graph format or XML, it's a tree. So you can't put recursions in it. or cyclic references. It's not possible. The format can't handle it. So you have to put copies everywhere. So it gets big and slow. Yeah. Of course, it's a bigger format, so parsing is needed. So you can't just handle small, quick byte reading. You have to parse actual code, and that's slow. And it's not suited for really huge amounts of data. And the circle reference cannot be handled because the format doesn't, or the formats are not graphs, but actual trees. Yeah. So Brian Getz had a proposal. He talked a lot of the JDK guys, and it's an Amber project. It's just an idea, a proposal. There's no API yet. It's some years old, like now. And it does a lot of stuff better than the actual serialization, but it has a lot of conceptual errors, again, in my opinion. It still breaks referential integrity. It doesn't separate concerns. It's baked in a JDK again. And it's still a draft, not an implementation or an actual project at the JDK. So, and we looked at the serialization features and thought we want to create an engine to store object graphs. So we have to serialize them somehow. And we looked at the available solutions, and we said we have to do it ourselves, because all the limitations of the current serialization frameworks didn't enable us to build the storage engine like we wanted to. So we built a new serialization from ground up, which is used for the storage engine called Eclipse Store. It's an open source project as well. And it was designed to eliminate the shortcomings of the existing serialization frameworks. And the key points we had in mind were security, flexibility, and performance. So what did we do differently? First of all, we separated data and metadata, meaning the description of the classes is not built into the data stream itself. If you send over data with the Java serialization, you have the class descriptions and data in one stream. And this is a needless overhead and a security vulnerability, because you can manipulate the object description, which is bad by itself. Yeah. And it's not flexible. And we don't execute code at deserializations. We don't use constructors or any initializers. We never call any code. And so you can inject malicious code like you want to, it's never executed. So this makes basically injecting malicious code impossible at this point. And we use a technique called swizzling. It's an actual thing, and you can look it up on Wikipedia. We map objects internally to unique IDs, just a long value. And with this swizzling, this object ID mapping, we can always restore the referential integrity, even in bigger object graphs. So we can read and write parts of an object graph and merge it into the live graph, knowing where it belongs. Because of this feature, we always know what object is mapped to what ID. And it's used to as well for indexation. So the storage data of which our serializer creates, the binary data, is automatically indexed because we have this ID mapping. And the storage engine later on, which uses our serializer, always knows where what object lives. So it's a built-in indexing. So you can have gigabytes or terabytes of data on your hard drive, and if you request one specific object, the storage engine knows, in this file, I have to look, only reads a bit and can deserialize this exact object without scanning all the binary data. So how does it work? On every initialization, the serialization engine analyzes the current runtime's version of the classes which it discovers. So let's say you serialize a customer, the engine says, oh, the customer, a new type for me. So then it creates a metadata from the class description. So it does a reflection once for this object, for this specific class. And after that, only this metadata layer is accessed. So basically the reflection is cached in a running JVM. So reflection was slow in older JDK versions, but nowadays it's fast, and we don't need to pre-analyze the types with pre-compilation and stuff like that, because it's quick enough and it's done once anyway, and afterwards the cache is accessed for the metadata. At this point, if the class layout changes, let's say you deployed a version 2 of your project, you added a field to your customer, but in a storage data or in your binary data somewhere is still the old version of this customer. So we have to do versioning, and this is done at this stage as well. We create a type lineage, meaning we know the mapping from each version, from type A version 1 to type A version 2, version 3, and so on, every time. So you can change your classes as you like. Add fields, move fields, rename classes, whatever you do. You can map it in a metadata layer, and the serialization engine can convert data from different software versions. Yeah. So, and then we do a lot of off-heap stuff, meaning we utilize the area of the memory area of the JVM, which is not bothered by the garbage collector and can be paged by the operating system. So if you run out of memory on a heap, you get an out of memory error. But the off-heap region can be paged by the operating system, and so you don't run out of memory, and the garbage collector doesn't have to scan through it, because this is just a bunch of bytes lying around somewhere in the memory, and it's managed by the serialization engine. So we have kind of a binary cache off heap and create objects out of this cache. And this is the fastest possible way, because we do low-level byte operations. We only copy bytes from off heap to heap. We say, hey, JDK or JVM, we want to create a new object, and we get it memory address on a heap. And on this memory address, we copy just bytes, primitives, ints and doubles and longs and pointers, which are just longs as well. And that's what an object is, just a series of bytes. And then we tell the JVM, create a new object. And all the JVM does is using this memory address as a new object, and the fields are populated automatically. And no code is executed. And it's the fastest possible way to create objects in a JVM without executing code, and the most secure way as well. So it's a lot of low-level stuff we're using, but we had to do it because we wanted to be quick and secure. A lot of people ask then, what will happen if the unsafe goes away? Do you know unsafe in a JDK, the class? It's an unofficial API for low-level memory operations. So, but unsafe is used by so many frameworks, they just can't throw it out. What they do is they're replacing in the unsafe class with public API. The foreign function and memory API, for example, or method handlers will replace the unsafe with an official API, so we are safe using this low-level memory stuff and don't have to be afraid for the future. So, And by separating the metadata and data layer and by using external handlers, we have no limitations regarding what object can be serialized. Meaning the Java serialization, if you use this one, you have to define the serialization, customization inside this class. If you have a customer, you have to write your serialization code inside your customer class. If you don't own the customer code, because you use third-party libraries, you cannot do it. So we said we have to use external handlers, meaning you don't have serialization code built into your Pochos, but you write an external handler for that and register the handle mapped to your Pocho type. You have a customer handler mapped to a Pocho customer class externally. So you can use third-party libraries. Let's say you have a super-duper collection list. Then you write a super-duper collection list handler for that and map it in a registry. So you can customize external libraries as well. And we don't have any requirements for your code. You don't need special interfaces or superclasses or annotations, nothing. It's all done in a handler. So you don't pollute your business code with technical details. Yeah. And the depth of your object graph is not limited as well, so you can serialize really complex graphs. This was a requirement as well for our storage engine, because we wanted to handle really huge graphs as well. Most of the serialization frameworks out there use stack-based recursion, meaning pointer by pointer, they call new methods. And the stack grows on, and if a stack limit is reached, you get a Stack Overflow error, and your JVM crashes. If you have a huge object graph, we don't do that. We have different phases of deserialization, and only have one stack per phase. So you can have complex graphs like you like. And we can cover changes through the, we call it internally legacy type mapping, where you can define different versions of your types, so you can convert through the life cycle of your application and don't break the binary data. We reached, thanks to the low-level byte handling stuff, we have a superior performance as well. The native byte format we are using for this, the serialized data is basically the same that JVM has on a heap itself. So we don't have to do a lot of conversion. It's basically just a byte copying from memory to a socket or to a stream or to files or whatever. Yeah. So benefits, of course, are it's easy to use. It's pure Java, no external dependencies. The only one we have inside is the logging facade. You don't have to use internal configuration, like I said several times, just use external handlers. I will show you some code. Any object can be serialized even by third parties. It fits seamlessly into the Java object model, and you don't pollute your business classes without technical details. It's secure, it's fast, and it's open source and available at Maven Central and on GitHub. So let's see some code. The dependency currently is version 2. Of course, you can use the build tool of your choice. You don't have to use Maven if you don't like. And that's all about serialization. You have several medium formats we support. The most commonly used, of course, will be byte arrays. A different format we provide is byte buffers, which are living off heap. But most of the time a byte array format will be good enough, because you can put byte arrays in any stream file or whatever transport layer you have. And that will be the most used, I guess. So And of course, you have two methods. You'll be using all the time serialize, deserialize. You get your binary format, your transport format, and then you deserialize it back. So this is the most rudimentary code you'll see in that, but you can customize it down to the last byte. This whole engine is interface-based. The API is interface-based designed. So you can exchange every single aspect of the engine if you like. But most of the time, what you will customize are type handlers. What type handlers do, they define for one specific type how it's how the binaries are created and the objects are created for one certain type. And then you can optimize the performance and the memory consumption. If you have really complex objects where our built-in type handlers are not quick enough or create too big a code, you can build custom type handlers for that. Let's say, for example, we do have a class called timeslot for time series database. We have a software which gets millions of measuring data put in a system per second. So there is a lot of time slot instances in your data stream. What our generic type analyzer will do, it looks at the object and says, I have a primitive. I will put the primitive directly in the time slot record. But then I got two new objects. Each object is a new record for me because I don't want to break the referential integrity. So what the serializer does, it creates actually 3 records out of this one single time slot because you have 3 objects. Yeah. So you have an object ID, then you have a type ID, and then comes the data. One is a slot number, and then these 2 date references, which are just type IDs and longs, which map to these 2 date instances. And they internally have, of course, a timestamp. That's what a date is internally. Yeah. So we got 3 records in a binary format of the serializer for one single type, but we want to optimize it and say, hey, we just inline the 2 timestamps in the time slot, and we create the date instances just out of this timestamp. That's what we want to do. We want to compress the serial format, basically a compression algorithm, because in our time series database we don't care about referential integrity for date instances. Who does in that case? So there are several ways you can define type handlers. For a simple case like like that, you could either put a static method into your code if you own the code, or you can write an external type and register this type in the builder of the serializer. And you just have to define a binary type handler which handles a certain type, and then you define fields. You always have primitive fields, of course, in a record. The field name and the serializing and deserializing functions. So you return a primitive, and on the other hand, you populate the field with the primitive value, and that's all about it. You write bytes and you restore data from bytes, and that's all a serializer does. So, and there you can see, you can basically compress your format from this to this. I'd say it's a third of the original data. So you have a really good compression by one single optimization for one single type. You can get a lot more out of the engine. You have for external handler, I had an example for the buffered image type in a JDK. We can say, hey, while storing the data, we store bytes encoded to a PNG format. So because you don't want to serialize all the internal stuff of a buffered image, we want to encode it into an image format, and we want to decode it back so you can use PNG, JPEG, whatever you like, and put even bigger binary stuff into your data stream. It's just a example how to use external type handlers. So you don't have to pollute your classes. And like I told you, we can do the legacy type mapping. We say we have a new version of the person, which has 2 fields for the name. And for this, you can define legacy type handler or legacy type mappers, depending if you want to do a structural change or a type change. And every case can be handled by just registering your custom handlers. Most of the common cases can be handled by the engine automatically. If you have primitive changes, let's say you change an int to a long, or a float to a double, the engine can convert the data without data loss, so it does it automatically. But if the engine cannot decide automatically what to do, like conversion from name to 2 fields, you have to provide a mapping for that. So, because we are separating metadata and the actual data, both sides have to know the metadata to convert and convert the classes from the binary form. If you don't have the possibility to control both sides, you have to send the metadata as well to the receiving side, and that's what the typed serializer is for. Only difference is the serialization. The serializer type, the interface is the same. This one sends the metadata in a stream as well if you need to. If you can control both sides, sender and receiver, you can leave out the metadata and just use the plain serializer, not the typed serializer. But for this case, the typed serializer is a new implementation as well. All right, so running out of time. I have some links. The GitHub site of the serializer and the store projects and the official website where you can look it up. You can check it out. We have examples online and extensive documentation for the storage engine and serializer, and a lot of examples in the repository as well, in the Eclipse store repository. And these are good starting points if you want to check it out and try around. Yeah. All right. So thanks. That's it from my side. If you have any questions, I guess we can stay here for a few minutes. On the other side, I can wait outside. Yeah. We don't have a stream implementation yet. It's an open issue, but we provide you can use default output streams and put the bytes in there. So you have to build around, but we don't have a stream implementation yet. But I think it's a matter of time, because we just have to create a custom input stream where the serializer lives inside here. And you can put a write object which uses our serializer. Yeah. Default implementation for the leave out this field function is transient, yeah. But if you want to use a different criteria for that, let's say underscore at the name, you can inject a different criteria for that. So, but default criteria is transient. Yeah. For some cases, yeah. If you want to use records, for example, and you use a model system, you have to export the base module. Yeah. Yeah. It's a limitation at the records. The records are analyzed differently by reflection. I don't know why they did it, but you have to export the base module in order to get it to work. Yeah. Yeah. Yeah, you can use every JVM language you like. Yeah. We have projects with Kotlin and Scala, to my knowledge. Yeah. Yeah. All right. So thanks a lot, and see you around.